Hello, all you calculus students. Today we're going to be discussing Handout 14, and in Handout 14 we will be talking about the mean value theorem, and then later on we'll be talking about the different graph shapes and how derivatives affect the shape of graphs. And this will be section 4.2 and section 4.3 in your text. And so we are looking to understand the mean value theorem, but first we got to go over Rolle's theorem, which will help us to get to the point where we can understand the mean value theorem, kind of a gentle step up, if you will. So Rolle's theorem, it has three preconditions before we can get to the conclusion down here. So let's go ahead and walk through our three conditions. Our condition one is that our function f of x is continuous on the interval from a to b. So once again, x has got to be in between a and b. And so our interval, let's go and just draw it out here. And x lives somewhere inside of there. Okay. Our next condition is that our function f of x is differentiable on the interval. And you can tell if it's differentiable or not by looking at the graph, by simply noting if there's no corner points. It's all not only continuous but smooth and continuous. So, a graph of a differentiable function will be smooth. Alright, our third condition is that the endpoints f of a must equal f of b. So whatever your function is at, the y value, it's got to end at that same point. Alright, so if these three conditions are met, then there exists a value, c, that is somewhere in between. So c is some point in between those two, such that the derivative evaluated at that point will be 0. That is, it will come back down. You can kind of already see from our graph here that our derivative is 0 here, our derivative would be 0 here, and our derivative would be 0 there. So it doesn't have to be just one point, it can be multiple points. So let's go ahead and take a look at some of these graphs. Note that this guy here is, flat across. F prime at 3 equals 0, clearly. Alright? And note that, that's the conclusion, but were the three conditions met? Yes, they were. F of a and f of b were at the same point. Our function is continuous, there are no jumps. And it is also quite smooth. Alright, let's look at this next guy. We see condition 1, the function is continuous along here. Right? It is smooth. There are no jumps or anything like that. Nothing like this. And f of a equals f of b. And so where does the derivative of our function equal 0? Well, it equals 0 over the entire duration. Right? It's just a horizontal line. Alright, so let's take a look at this guy right here. Let's look at our three conditions. The function is continuous. There are no jumps. I can trace it with my pen. It is smooth. There are no corner points. There's nothing that looks like this. Right? Everything is a nice kind of smooth transition. I could rub my finger along the edge of the graph and not come across any corner points. The last condition, f of a equals f of b. So that last condition is met. All three conditions are met, and so that means we are guaranteed that we will have a derivative at 0 at least one point, And note we've got a point here where the derivative is 0. Right here, the derivative is 0. And right here, the derivative is 0. So we actually have 3 points right there where the derivative is 0. Okay, and so that's all the Rolle's theorem. And that's the warm-up for the mean value theorem. Rolle's theorem, as you can see, had 3 conditions. Mean value theorem only has 2. First condition, much like Rolle's theorem, f of x is continuous. Note how this seems to be a theme. Second condition, f of x is differentiable. Right, so note that the conditions are very similar. But they are slightly relaxed. We don't have that third conditions. F of A and f of B do not have to be equal to each other. So this theorem is a little bit more flexible for that reason. So if these 2 conditions are met, then there exists a value, x equals c, that is in between a and b. Once again, c is in between a and b, such that the derivative is equal to the average slope. And so basically stated right here, the derivative at some value c equals the average slope. And what is the average slope? F of b minus f of a, all over b minus a. Okay, so once again, if these 2 conditions are met, we're guaranteed that at some point the derivative will be equal to the average slope in between the end points. Alright, so here I've put together an interactive demonstration for you. This is available in the module with this handout. Here, basically, we've got a function going from a to b. Right now, it's from 0 to a little past almost to 6.5. But I've got it set up to where you can modify the endpoints. And note, if you change up the endpoints, that affects the average slope in between them. Okay. And so what this guy does is it calculates the average slope in between the endpoints right here, and then we have this our tangent line right here. And so you can kind of go through and try and figure out, okay, where is this the mean value theorem satisfied? What is our value c? And so you can see it right there. That's one value where the derivative is equal to the average slope in between. And you can kind of go along a little further. Find some other points. There it looks like we got a good one right there. And again, this line has the average slope from in between a and b. And the derivative right there will be the same as the average slope. So that's another spot where our mean value theorem is satisfied, and there are others. So kind of go through this, play around with it, mess with the settings, and see where you can find where the mean value theorem is satisfied on your own. Okay, so back to the handout. We have another theorem on our hands, and this theorem states that if f of prime equals g of prime, then the actual function over here only differs by a constant. So let's go ahead and verify this with an example. We have f, and that prime should not be there. Go ahead and redact that. It should just read f of x equals x squared minus 300. And then g of x equals x squared plus 500. So let's calculate f prime of x. And so when we calculate f prime, that is 2x. And then g prime of x also equals 2x. So note that these two guys, when you look, or these two guys up here, the difference between them is only a constant. Okay, so now on to the back side of the handout where we get to section 4.3. What derivatives tell us about the shapes of graphs. So we start off with 3 conditions. If our derivative is greater than 0, then f of x is increasing. If f prime of x equals 0, then f of x is constant. And finally, if f prime of x is less than 0, then our function is decreasing. We've already kind of gone over that quite a bit. This should be old hat by now. So let's go ahead and look at the first derivative test. If our derivative changes sign at x equals c, then f of c is a local extremum. And that simply means that, extremum. And that simply means that we would have a local max or a local min. That's what extremum means. And so, note what's going on. Kind of look at a graph like this. Note this is a local max here, local min here. The derivative was positive here and negative here. It changed sign. And then once again down here, local min, it was negative, and then it became positive. And so anytime your derivative changes sign at a value, that's before the value and after the value, then that's an indicator that you have either a local max or a local min. And so we note that if the derivative changes from negative to positive, well, then we've got a local min. And if you go from positive to negative, like you do here, well, then you have a local max. All right, and so this is what's known as the first derivative test, and you can use it to identify it where you have local maxes and local mins. And all you have to do is first identify when the derivative is 0, and then figure out how it changes sign, or how and if it changes sign before and after. For instance, y equals x cubed. It's got a first derivative of 3x squared. This does equal 0 at x when x is 0 itself, but it does not change sign. So there's no max or min. And if you recall from the graph, it looks like that. There is no local max or min. So just because a derivative is 0, that does not mean that you've got a local max or a min. It has to change signs for that to be the case. All right, so now we're going to go over a definition. The graph of a function is concave up on an interval if it is above all tangent lines on that interval. And you can think of concave as a number of different things. Concave just basically means it's kind of curving, up like this. That'd be a concave up situation. And so any tangent line will always be below it, right? The function will always be above the tangent line. All right, so I've got another interactive demonstration for you guys to play with. Note this is just simply the graph of x squared here. And you can move the tangent line wherever you want. Does not matter where you move it. The function, other than the point of contact, of course. But outside of that, the function is above all points of the tangent line. Now, this is for concave up. What about concave down? What about a function that is concave down? Well, let's look at one. This is clearly concave down. If it were a cup, or a bowl, the contents would be spilled out. And you can see that the function is below all the points of the tangent line. So we've got a nice definition for something that is concave down as well. For something to be concave down, the function is below all points of the tangent line, except, of course, the point of contact. So as to the question, when is a function concave down? Well, it is concave down when the function is below the tangent line. All right. Now I've got one more interactive demonstration on this, but before I want to talk about the inflection point. The inflection point is where f of x changes its concavity. It could go from being a concave up, a positive concavity, or it could go to a concave down, a negative concavity, or could be, going really concave, and then all of a sudden it becomes, not concave at a point, neither concave up or concave down. All right, so an inflection point, note what happens. You have an inflection point anytime your second derivative equals 0. That would be called an inflection point. So let's look at a graph. And it's going to be a graph of this part right here. Note we already looked at this graph. So let's go on over. And so we've got, at some points along the way, this function is concave down, and other points it's concave up. And so if you note that along this interval right here, the function is entirely below the tangent line, and it seems to go along this pattern, still below, until we hit about right here. Then as we travel along, the function becomes concave up. And note that the point where it changes concavity is about right here. That's our inflection point, right here. And if we look at the second derivative of this guy, and we'll call this for lack of a better term, h of x, and that equals the derivative of the derivative. And so note that this inflection point corresponds with when this graph right here becomes 0. And so you can see right there, 1.667, and it comes straight down. X equals 1.667. That would be our inflection point. That is the point where the graph switches from being concave down to becoming concave up. And so this brings us to our concavity test. If the second derivative of f of x is greater than 0 on an interval, then the function is concave up on that interval. And if f double prime of x is, well, they can't both be greater than 0. Less than 0 on an interval, then we are concave down. And so going back to our graph that we're looking at before, note where the second derivative is negative in this zone right here, that our function is indeed concave down during that period. And when our second derivative is positive here, well, then our function becomes concave up. And you can also see this with this guy here. Note that the second derivative of this guy would simply be -2. And so, in fact, it is concave down everywhere. And so this brings us to everything that we need for the second derivative test. If the first derivative equals 0 and the second derivative is greater than 0, then x equals c is a local min. And you can think this through. What does this guy mean right here? Well, it means that it's concave up, right? That's what concave up looks like. And does this guy right here, at that point, well, that's a derivative of 0, and that gives us a local min. So that's why we say that it would be a local min here. And that's the first part. The second part, if our derivative is equal to 0, again, and this time we say if the second derivative is less than 0, then we have a local max. And let's think about the picture of this. If the second derivative is less than 0, that means it's concave down. At the point where the derivative is 0, that's where it changes from increasing to decreasing, and that gives us our local max right there. Okay, and this is the second derivative test. Let's do a few examples now. All right, so on A, the easiest thing to do is apply the first derivative test. And so we simply take the derivative one time. First derivative of x equals 3x squared. All right? And so we note that when does this equal 0? This equals 0 whenever x is 0. So that's going to be we'll call that our c. All right, so what happens right before 0 and what happens right after 0? Well, note that we're dealing with a square function. So right before 0, it's positive. Right after 0, it's positive. So we would say no extremum. Okay. All right, so that one's pretty straightforward. Apply the second derivative test to this guy here. This is our g of x. So we have to take the derivative twice. G prime of x equals 2x times ex squared. Again, that's using the chain rule. And then we take the second derivative. And now we're going to use the product rule. All right, so here's our function 1. Here is function 2 for the product rule. And so the derivative of 2x is simply 2 times e to the x squared. And then the second guy, we've got 2x multiplied by 2x ex squared. That's the derivative of the second guy. All right, so let's go ahead and reduce this down. G double prime of x, we can factor out a 2e to the x squared. And that leaves us with 1 plus 2x squared right here. Okay, so we've got a nice setup. So first we want to figure out, okay, what value of c makes this equal to 0? Well, look right there. It's going to be 0 itself. So c equals 0. So now we plug this into the second derivative to see what's going on there. And we plug it in, we get 2 times 1 plus 0, which equals 2. And that's greater than 0. That tells us we are concave up, meaning we got a shape kind of like this at the value 0. So we would say we have a local min at x equals 0. Okay, very good. So now we need to look at the second derivative. Of x. And so again, we're simply just taking the derivative of everything in the first derivative. So we have 2 minus 0 minus, now it's going to be plus 1 over x squared. And then that's to do because 1 over x is the same thing as x to the negative first power. Okay, so now let's go ahead and plug in our different values for c and see if we get a positive or a negative number. So t double prime of negative 1/2, that gets us 2 plus 1 over negative 1/2 quantity squared. So it's going to be the sum of two positive numbers. That's greater than 0. So negative 1/2 is going to be at a point where we're concave up, meaning we're going to have a local min. And so t double prime at 1, that's the other one. We have 2 plus 1 over 1 squared. Well, that's also going to be greater than 0. So again, that's going to be concave up. Right? It's going to have this shape at negative 1/2, and it'll also have this shape at positive 1. So we have a local min at x equals, or should I say mins, at negative 1/2 and positive 1. Okay, so let's go ahead and take a look at a graph of these by everything. All right, here you can see that we were looking at the graph of x cubed. We note that there are no local maxes or mins along here, just as we predicted, even though the first derivative of our function is 0 right there, as you can plainly see. But the, sorry, I think he's moving around on me. Even though the first derivative is 0 at this point right here, that does not mean that we have a local max or a local min. And that's, because the derivative does not change signs. It stays positive before and it stays positive after. And if you were to apply the second derivative test, you would notice that the second derivative here is 0 as well. So it kind of brings up an excellent point. If the second derivative equals 0, then the second derivative test is inconclusive. And you have to rely more on the first derivative test in this case. All right, so let's look at our next example. E raised to the x squared. And here we notice that we do in fact have a local min as predicted. When we found the first derivative, we note that at 0, the derivative is 0. We note that it does change sign before and after, negative to a positive. And then we took the second derivative, and we can see at that point that it is indeed positive. And so, which led us to our local min conclusion. Now the next guy we note that indeed we do have a local mins at 0.5, or negative 0.5, and at positive 1. And you can see from the derivative here, we found zeros here and here, and then when we took the second derivative, we see that in both cases we got a positive value. And so that was our second derivative test. All right, so that's it. That's the handout. We went over 2 sections today. Section 4.2, the mean value theorem. And then we also went over the first and second derivative tests. Make sure you are ready for those by exam 3. So anyways, have a good day, and hopefully I will see you all soon.